I'm Carl-Johan Åström and I'm a senior professor in the Department of Automatic Control at Lund University.
And I'm Margaret Bauer and I'm the Lise Meitner professor at the Department of Automatic Control here in Lund, and I'm also a professor of process automation in Hamburg. And I am so happy, I'm so fortunate to be here in this incredibly stimulating environment that you have created here at this university.
You should also mention that Lise Meitner is a very prestigious appointment. But you're too shy to say that. If we start with this room, there is an automatic control system that keeps the temperature constant in this room. And when you came here, you probably had a car. And the car has most cars now have automatic speed control. So you can push a button and then the control goes at constant speed. If you are at home, you have a television at home. In the television system, there are lots of feedback systems that make sure that the sound level is right and that the picture is fine. And also internally in a television, there are lots of control systems sitting there.
Automatic control, our modern life depends on it because it's in every single system that we use. Yeah. If you look at chemical production, you have hundreds, if not thousands, control loops in every single production site that people are not aware of, and without which we wouldn't be able to produce efficiently and effectively.
Production of paper, production of electricity, production of food. So you can take all production processes, they depend critically on having control systems. Power system, you know, when we generate electricity, the plants that generate electricity, they would not function without control. And also when you generate electricity, you have to send it out on the net. And there are lots of control systems that are controlling the transmission of energy.
Then you also have wastewater treatment plants, so increasingly more and more countries like Sweden and Germany will recycle their water. Sweden and Germany are doing it already, but many countries don't recycle their water at this point in time. They just put it back into rivers, the dirty water. So having an irrigation plant, you have to make sure that you clean the water sufficiently. You have to use certain mechanisms such as flotation to get rid of impurities, and there we need loads of controls. If you think about it, in social media, you put out a new post on your favorite platform, Instagram or Facebook or LinkedIn, and you observe the reactions. We talk about time constants a lot, and that's an example of a time constant. How many people are reacting in what time? And control theory provides a basic structure to analyze this behavior. So it can potentially be very powerful to understand these networks.
And also if you look at your own body, you have the ability to balance when you're standing upright. And there's a feedback system that allows you to do this. And also when you're walking, there is a lot of feedback in the human body that allows you to walk at different speeds, and you can run very fast. Some people can stand on a line and balance, for example. And there are many control systems in the body, and you have several good examples of it.
Yeah. I mean, there are loads of examples, and I think that's really conundrum with control because it's so intuitive. I mean, babies can't stand up because when they're born they can't stand up, but as they grow, they learn how to control their bodies so they can stand. And we've all learned how to stand and how to speak. We're controlling our temperature in our body without knowing it. And it's the most intuitive thing, but yet it's not known to most people that they're actually doing control the whole time. So automatic control is called the hidden technology sometimes because it's there everywhere and we don't see it, we don't know about it, we don't know of it. It's not as obvious to everyone and people don't talk about it. I think it's partly because it's an enabler to achieve a certain goal. We are enabling something to make another system work and for other system to make a plan, and then the control is the technology that allows it to follow up on that plan. That's your invention, the hidden technology.
Now, I wanted to find a catchy name, for a talk at a conference. I thought it's hidden because it's used practically everywhere, but most people don't talk about it. So that's why you call it the hidden technology. That's one reason for it.
And I think it's also because the mathematical foundation behind that is something that is quite, it's more of a complex construct. So the main principle of automatic control is the feedback loop, that you take a measurement and you compare it against a certain wanted behavior. And comparing just means subtraction. It doesn't mean anything complicated. You're just subtracting the two. You look at the difference between the two, and then you make a decision, and you will act on your process will update, and it will go round, and that's the negative feedback loop.
So you can say control is this magic thing which sits between the sensor and the actuator.
Yeah, I like that you say magic, because it really is magic.
Yeah.
It's something that is so intuitive and natural, but it feels like magic when you do it. Control is a very mature technology in some industries, in the process industry, for example. There are some very exciting new applications of control where we're not quite sure where it's going to lead us. So, for example, in the biomedical arena, where we're having control systems that help us make a decision, for example, on diabetes, or on a heart rate control, or other control systems that are not so much in place. So we don't have such an established framework on how to implement it.
There is actually a common theoretical framework that could cover all the fields, and that's basically mathematics. So it's a common mathematics that can deal with all sorts of fields. For example, I started with military, with missile guidance, and then I worked to control a paper factory after that. And one can use a similar type of ideas, which is quite amazing. And it actually took a while before people discovered. You know, people who were doing process control and people who were in electric system, when they got together, they suddenly discovered we're actually doing the same thing, which is amazing. And what brought it together was the war, because in the war effort, you brought people from different fields together. And then the first books of control came out, and the United States did this very well, because after the effort, they decided to publish everything. So they published books, about 30 books of technology, radar system, radar navigations. And then they published one of the first control books, which is this one, called The Theory of Servo Mechanisms, which was published in 1947. And then what happened was that people discovered that control was so useful. So then it was introduced in education. It spread like wildfire all over the world.
I think the wonderful thing about automatic control is that it doesn't cost anything in terms of resources. It's a mathematical tool to improve any process that you have. And you make sure a process runs more smoothly, more efficiently, more energy efficient by using a very clever control algorithm. So you can save electricity, or you can save resources by doing very good control. So inherently, control is there to provide a more sustainable future.
But you have to pay for the computer.
Yes, you do have to pay for the
it's not infinitely cheap.
It's not infinitely cheap, but compared to what we use the computer for.
And also modeling. You know, modeling has played an important role in the whole climate debate. For example, when you figure out the way we are wasting nature right now, that was uncovered very, very well by mathematical models. So even if it's not control per se, the mathematical modeling has played a very major role in the whole climate debate. And something that's interesting, you know, if you talk about computers, I remember I worked for IBM in the math department in Yorktown Heights. And the leader of the department, he said something like this: when things change by 2 orders of magnitude, it is not evolution, it is revolution. And then if you combine this with Moore's law in computers, you have a revolution every 10 years. So in other words, computations get 100 times more powerful every 10 years. But we have not been able to capitalize on the computing power we have. And nowadays there are things, you know, like learning systems and things like this. You know, you talk a lot about AI today, for example, and machine learning. And AI is a funny business because it goes up and down like this. You know, there are lots of hypes. And right now there's a hype in machine learning. Will this materialize so that we are getting something that will really improve our working efficiency by a factor of 5 or something like this, or not? Nobody knows, but maybe. We made some progress, but it's a wide gap.
Yeah.
Which means opportunities.